logarithms. What exactly are logarithms? Well, let's find that out. To understand logarithms, you need to go back and think about exponential functions. For example, y equals 2 to the x. And just take note of some things about this exponential function. Notice it's always increasing here. It has a domain, negative infinity to infinity. You can put in any of these x values. And it has a range 0 to infinity. So it has a vertical asymptote there, a horizontal asymptote at y equals 0. And it never gets to 0, right? So the function goes from 0 to infinity, but it's never at 0. So this is the domain and the range of the exponential function. Now, notice this exponential function is 1 to 1. That means not only does every x correspond to exactly 1y, but every y corresponds to exactly 1x. It passes the horizontal and the vertical line test. Okay, it's a function, and in particular, it's a 1-to-1 function. Now, what's important about that is 1-to-1 functions have inverse functions. In other words, we know that there exists some function that if you take this line y equals x, there is some function that's like a mirror image across this line y equals x that looks something like this, right? And notice this inverse function is going to have a domain and range where, now remember, inverse functions, if you take the domain of 2 to the x, that's going to be the range of its inverse. So the range is going to be negative infinity to infinity. And sure enough, look at this little blue curve here. It goes down forever and up forever. Negative infinity to infinity. Now its domain is going to be like the range of 2 to the x. Okay, so this one is going to start at 0, but not at 0. Just, it's going to go from 0 to infinity, not including 0, and that will be the domain. So we know that this thing exists. We just need to know what to call it. Well, what we call it is log base 2 of x. Okay? Log, short for logarithm. Okay? Now, let's just look at this a little more. Let's suppose, to be clear, if we have a to the x, this is just an exponential function, and we want to talk about its inverse. Its inverse is log base a of x, like this. This is the inverse. Now, usually, we won't write f inverse of x when we're talking about a log. It's its own function. We'll just write f of x equals log base a of x. But I'm using the inverse notation here to emphasize that these are inverses of each other. Now, for example, if we have 3 to the x, well, its inverse would look like this, log base 3 of x. We had e to the x. There's that e. E is a very important number. Pops up a lot. The more you study mathematics, the more you see e popping up. Some very interesting places. So instead of writing log base e of x, we're just going to write ln x. Natural log of x. That's what it stands for, natural log of x. We just call it the natural log. Now, since we are a base 10 number system, where we have 10 to the x, instead of writing log base 10 of x, we'll just call this special log log x. And leaving off this 10 down here, we know, okay, we leave off this the little subscript down here, the base, we know that's base 10, and we call that the common log. Okay, now let's think about how do we find the inverse? So if we have some function like this, a to the x, and we want to find its inverse, well, remember I changed notation because I don't want to lug around this f of x, and then I interchange the variables. Every y becomes an x and every x becomes a y, and then I solve it. Well, what mechanism do we have to solve that? Well, we don't. How do we solve such a thing? So what we do is we just say, well, I know the solution, y equals, that's the inverse. So I'm just going to call it this. Now, the reason I went through this is so you can see, yeah, this log base a of x, it's an exponent here. Because later on we're going to notice some properties of exponents, or properties of logs. And we're going to notice there's some similarities with the, it may remind us some of the properties of exponents. So it's good just to see this. Now, let's look at evaluating logs. Let's suppose we have something like this, an exponential situation here. We have 2 to the third equals 8. So it's sort of like we took this function 2 to the x and we plugged in a 3 and got out an 8, right? So 2 to the third is 8. So there's an ordered pair. This point is on this function. Now remember what the inverse does. The inverse is going to switch the ordered pairs. So the inverse of 2 to the x is log base 2 of x. And the ordered pair then would be this, 8, 3. See, this is 3, 8. We swap that and we get 8, 3. Now notice the output here, log base 2 of 8, is going to be the 3. Just like the output over here was 8. So the output and the inputs have been swapped. But here's what's happening. You may have to think about this a little bit. But what this is saying is 2, notice we've got the 2 and the 8, but what's left out? The 3. We're saying 2 to what power equals 8? Over here we were saying 2 to the third power equals 8. See, 2 to what power equals 8? Okay, so 2 to what power is equal to 8? Well, 3. So the evaluation here, 2 log base 2 of 8 is equal to 3. So let's look at some more. Log base 3 of 9. 3 to what power equals 9? 2. See? Just think about it a little bit. Log base 5. 5 to what power equals 25? 3. See? 5 to the third powers. Well, I said 25. 125. Okay. Okay, here's one of those, the common log here. Log base 10 of 100. This is saying 10 to what power equals 100? 2. Okay. Now, here's one, another common log. Log base 10 of 0.1. This is a little bit trickier. 10 to what power is 0.1? Well, think about it. 1 over 10 is 0.1. 10 to the negative 1 is 1 over 10, so this must be negative 1. See, 10 to the negative 1 is 0.1. Here's log base e. E to what power is e to the fourth? Well, 4, right? E to the fourth is e to the fourth. What about this? Look at this. 9 to what power is 3? Now remember, square roots, if you have a number raised to the 1/2 power, that's like taking the square root. So 25 to the 1/2 power is 5, the square root of 25. So we think in that term. So we say 9 to what power is 3? 1/2. There we are. So that's how we can evaluate these logs. Now, we want to look at an exponent and a log. We want to be able to go from exponential form to logarithmic form of an expression. So we have an exponential expression, we want to rise a logarithmic expression, and vice versa. Now remember this, that since these are inverses of each other, f of x equals a to the x, log base a of x, these are inverses of each other. And what that means is that f of g of x is equal to g of f of x is equal to x. That's what happens when you have two functions that are inverses of each other. When you take the composite of each, f of g and g of f, you get x. Okay, so let's look at this. F of g of x equals a to the log base a of x. See? I just replaced the x with log base a of x and equals x. And also, g of f of x, log base a of a to the x. Well, these things, log base a and a to the x, they kind of get rid of each other and we're just left with x. Now, we're not going to think through this every time. In other words, mentally, how we go from one form to the other is not thinking about this. This is just what's going on in the background. Let's suppose we have 2 to the third equals 8. Now, notice I can do this. I can apply log base 2 to both sides. But dig this now. Dig this. Log base 2, 2 to the third. All I'm going to be left with over here is 3. And there we have it. We've converted. We went from exponential form to now log form. 2 to the third power equals 8. And we start off with 2 to the third equals 8. Okay? So let's look at this. Now, so we're not thinking about that. I don't have to look at this and say, okay, I'm going to apply log base 2 to both sides. No. You can think of it this way. You can think, okay, I'm going to take the base right here and pull it out and put it to the other side. Now, as soon as it crosses that equal sign, it was the base of an exponent. Now it crosses over, and it's the base of a log. See, dig what I did there? I just pulled that 2 out, the 4 came down, and this became log base 2 of 16. See? Dig that. There it goes. So we've converted. So I've gone from exponential form to log form. So let's try this one. 2 to the 5th power equals 32. Well, I take log base 2 of 32 equals 5. See? I just took the 2, made it a base of the 2 of the log over here. See? So we're not every time consciously thinking, oh, okay, I'm applying log base 2 to both sides. Okay, let's try this one. 10 to the third equals 1,000. Well, I'm going to take the base here, make it a base of a log over here, and there we have it. See? Of course, I didn't write the base 10 over here because remember, this is common log. Okay, now, let's go the other way. Let's start with a log and change it to an exponent form. Okay, so notice what I'm going to do. I'm going to take this 2, bring it over here, and it becomes a base. It was a base of a log over here. Now it's going to become a base of an exponent over here. Here we go. 2. There it goes. See? Dig that. So I took the 2 out and the log just disappeared. Okay? And you're left with 16 over here, 2 to the 4th. Now, we know behind the scenes what's going on, but this is just the way we can think about it. Okay? Now, so let's look here. I'm going to take the 4, make it a base of an exponent over here, and we're just left with 64 equals 4 to the third. There we go. Look at this one. Okay, make the 10 to the second. Yeah, that's it. Now, whenever we're dealing with logarithmic functions, we have to be concerned with the domain. It's just like when we're dealing with even index radical functions, like the square root of x. We have to be mindful that the domain is x is greater than or equal to 0. Or when we're dealing with a rational function where we have an independent variable in the denominator, we have to be concerned, for example, 1 over x, we have to be mindful that x can never be 0. So with logs, we have a similar situation. Remember, what I've done here is I've just graphed the natural log of x as an example. Notice that it's asymptotic to the y-axis. In other words, the domain for the log normally goes from 0 to infinity, not including 0. So it's parentheses, 0 comma infinity. But let's suppose that we have something in here, in the radical, like x minus some number. Well, let's see what happens. Normally the asymptote is the y-axis, x equals 0. But let's see what happens. What if a is 1? Notice that now the domain is not 0 to infinity, it's 1 to infinity, right? See? You see the asymptote here? So the graph has been shifted over. Or if we make it 2, you can see how the graph is shifted over, so the domain changes. So if a is 4, the domain is 4 to infinity. Now we could go the other way. We could come back over here and say, well, what if a is negative 1? That would be x plus 1. Well, now in here, so now we say, okay, the domain would be negative 1 to infinity. And you can see how this works. See? As we change a, the domain changes. In other words, the domain is dependent upon what's inside this log. So here's the thing. With logarithms, you can never take the log of 0 or a negative number. So our concern when we have a logarithm like this one is that we never try to plug in anything that's going to result in us trying to take the log of 0 or the log of a negative number. So we have to do some investigation. So we take this 2x plus 3, set it greater than 0, and solve it. And we find this, that 2x plus 3 is going to be greater than 0 as long as x is greater than negative 3 halves. Or another way to write it in interval notation is this, negative 3 halves to infinity. Not including negative 3 halves, because that would be where the log, that would be where 2x plus 3 is 0. Okay, and here's what the graph looks like. Notice, here is the vertical asymptote, x equals negative 3 halves, and our function goes to the right of that. If we plug in any value for x over here, we're going to get 2x plus 3 to be positive. And that's what we want. If we go to the left of that asymptote, that won't work, because then we'll be trying to take the log of a negative number. Now, let's look at another one. G of x equals log base 3 of x squared minus 16. Once again, we're concerned, where does x squared minus 16, where is it greater than 0? Well, one of the ways that we might proceed with solving this one is just to consider, well, where are the transition points? Where does it go from being less than 0 to greater than 0, or greater than 0 to less than 0? Well, those happen here at the boundary. In other words, those happen wherever x squared minus 16 is equal to 0. So let me solve this, and then I'll use that to divide up the number line. But here's what we do. Let's just solve this one. I factor it, and I find that x equals plus or minus 4. Okay, so I just solved this simple quadratic equation. Now I use those boundary points to divide up the number line. Everything less than negative 4, everything greater than 4, and everything between negative 4 and 4. Those are the divisions here. So I pick representative numbers from each region. Negative 5 for everything less than negative 4, 0 for the region between, the interval between, and 5 for the interval, that region, the x values above 4. Okay? Then I test those. I plug in a negative 5. Dig what I have here now. I have negative 5 minus 4. That's negative. Negative 5 plus 4. That's negative. Negative times a negative is a positive. Jackpot. That's greater than 0. That's part of my region. That's part of my domain. This thing over here, this region right here is part of my domain. Now let's plug in the 0. When I put in a 0, I get a negative 4 times 4. That's negative. So that's not greater than 0. So we don't include that one. Let's try 5. Well, 5 minus 4 times 5 plus 4. Positive times a positive. That will work. So we get our domain. Negative infinity to negative 4. All of this region over here. Unioned with 4 to infinity. All of this over here. And here's what it looks like. We see our vertical asymptotes here. And the function goes off this way and this way. Let's look at 3 properties of logarithms that are going to make them a really powerful mathematical tool for us. First of all, let's think about this. Let's just consider this situation where we're going to let x equal log base a of u and y equal log base a of v, and u and v, let's just say, are positive real numbers. Now what I want to do, I want to convert both of them to exponent form. In other words, bring this a over and make it a base of a over here, so we have a to the x equals u, and over here a to the y equals v. Now I'm going to multiply a to the x and a to the y together, and that's the same as multiplying u times v. See? Now remember that when you have the same base, here you have a to the x, a to the y, you can just rewrite that as a to the x plus y. That's a property of exponents. Now that I've done that, I want to move this back to log form. Okay, so it's going to be log base a over here, x plus y equals log base a of uv. Now remember, y, see, x, x is log base a of u. See, look at that. So I can replace x with log base a of u, and I can replace y with log base a of v. And there I have it. Okay, now look what we've discovered here. This is a property of logarithms, that if you take the log of a product, it's equal to a sum of the logs. See? Log of a u times v is equal to log u plus log v. Now, this is provided you have the same base. See, we have the same base here. So, this is one of the properties of logs. Now, let's go back and look at this same thing. X equals log base a of u, y equals log base a of v. Let's convert these to exponent form, and this time we'll divide. Instead of multiplying a to the x times a to the y, we'll divide. So a to the x divided by a to the y is the same as u over v. Now, once again, we'll use a property of exponents to rewrite this as a to the x minus y. Now, let's convert it back to log form. See? So it's log base a of u over v and x minus y over here. Now, likewise, notice x equals log base a of u and y equals log base a of v. So let's make that change. Now look what we have. You have log of u over v is equal to log u minus log v. That's another property of logs that we'll use. Now, let's think about this situation here. Log base a of u to the fourth. Think about what that means. We could expand that out. U to the fourth is u times u times u times u. Now, we just learned a sum property for logs, that log of u times v is equal to log u plus log v. So let's apply that here, and we get log u plus log u plus log u plus log u, right? This is a property that we observed earlier. Now notice there are 4 of these. 1, 2, 3, 4. So this right here, of course, is log u to the fourth, and this right here is 4 log u. See, there's 4 of them. 1, 2, 3, 4. So look what this is saying. These two are the same. And in fact, this is our third property that we're going to observe, that log base a of u to the r is equal to r log base a of u. It's like I just brought that r out front. And then we put those together with our other 2 properties. And these are 3 very powerful tools in mathematics that we'll be using. Okay, so we've got these properties of logs. And I want to go through a few logarithmic expressions so that we can see how these properties can be used. So let's suppose that we have an expression like this. And we want to condense this expression using these properties to a log of a single quantity. So, notice that they're both base 2, which that's what we have to have. We have to have the same base. And notice we have a sum of logs. Well, that draws our attention up to this property. We can rewrite this as a single log of a product. So in other words, I could rewrite this as log base 2 of 3x. Okay, let's take a look at this one. Now we have a difference of logs. Log base 7, 3 minus log base 7x. This is a difference, so it's telling us, it's pointing us to this property. Now note that this is just log base 7 of 3 over x. It's not log base 7 of 3 over log base 7 of x. No, it's just one log here. A log of this quotient. That's what it is. Okay, let's try this one now. With this one, we've got a couple of things going on. We've got this plus here, which draws our attention to this property, but also we've got these coefficients in front of the logs, which makes us think of this property. Well, here's what we want to do. It's sort of like, you think of order of operations. Take care of the exponents first. In other words, what I need to do here is I need to bring the 3 up first. So I'm going to call this log base 5 of x cubed plus log base 5 y squared. See, take care of the exponents first. If you've got coefficients of the logs, go ahead and bring those up and make them exponents. Do that first. Then you come back, and now that's taken care of. Now we can go through here and take care of this sum. Like this. See, just put them together. Okay. Now, so here's the three properties. Let's go the other way. Let's suppose that we have a log, just one quantity here, and we want to expand the expression. In other words, we want to go backwards from what we just did. So we've got log base 2 of 7x. We write that as log base 2 of 7 plus log base 2 of x. Okay, using this property. We've got log base 10, this is a common log, 4 over x. So we want to use this property, right? Because if we've got log of something, u over v, we can write it this way. So we just break it apart that way. Okay, now, here's one. The natural log of the square root of xy. So let's take care of the exponent first. You might say, well, there's no exponent there. Yeah, there is, right? The square root. That's like xy to the 1/2. So let's view it that way. The log of xy to the 1/2. So we take care of this exponent part first. Okay, do that first. So I'll bring around the 1/2 to the front. Now I can break this apart. See, log xy. Now, so here we go. Now notice the 1/2 still applies to both of these. So what you wouldn't want to do is just say 1/2 log x plus log y and not have the parentheses here. See, the 1/2 applies to both of these. So I've got 1/2 log xy. This whole thing is expanded and it's multiplied by the 1/2. So be sure and put your little brackets there or your parentheses, whichever you prefer. Okay, let's look at this one. Here's another one. Once again, we've got that exponent. We've got to take care of that first. So I want to bring that around front, like that. Now, I'm going to expand this, and here's the deal. If it's on top, look, if you have something on the bottom, like this z, there's going to be a minus in front of that log. If it's on top, it's going to be a plus. So what you're going to do is, if you see it on the bottom, there's going to be a minus in front. So let's see how this is going to look. You're going to have 7 log x plus log y. How do you deal with this bottom? Minus log z. See? Because it came from the bottom. So you're going to have a minus. We're going to look at a change of base formula for logarithms. Now, this used to be really important. Like, for example, calculators would typically only have base 10 or base e. So if you had a log of base 2, you would need to convert it to either base 10 or base e to be able to, compute values with your calculator. Also, before even calculators, people would find values for logs from tables. Well, they didn't have tables for every single base. There's an infinite number of bases for logs, so you would need to convert from one base to a base where you could go to a table. Maybe you'd take a log in base 2 and convert it to base 10, so you could look up the values in a table of logs. But anyway, the change of base formula is something that's still important. Let's look at y equals log base a of x, and let's just explore how we might go about changing that to another base. First of all, let's convert it to exponential form. So in other words, instead of y equals log base a of x, I'll have a to the y equals x. Just, applying base a to both sides, we get this. Now, once I do that, let me go ahead and just apply base b to both sides. So I'm going to take log base b of the left side, log base b of the right side. See that? Now, look at this. I've got log base b of a to the y. let me bring the y out front. That's a property of logs. And then divide by log base b of a. There, look at that. And you might think, what'd you do that for? Well, notice that y is log base a of x. So, all of this is log base a of x. Now notice, all of this over here is log base b. This is log base a. So really, if I want it to convert from log base a to log base b, this is the way to do it. So, dig this. I've got log base 3 of x. That's the same as log base 4 of x over log base 4 of 3. Notice, if I want to convert log base 3 to log base 4, I'm going to have a fraction. Log base 4 on top, log base 4 on bottom. The top is going to have the x right here. The bottom is going to have the base. Okay, let's convert to another base. Here's base 7. Notice, log base 7x over log base 7 3. Notice the base is always on the bottom here. The base that was. Okay, so I'm going from log base 3 to log base 7. Okay, here's log base 10. See? Log base e. So it's just a formula, really, and it can be helpful sometimes. If you have an expression, for example, just simple. If your answer doesn't match the answer in the back of the book, if you're working a problem, maybe it's just you're in a different base. So it's an important thing to be able to go from one base to another. If nothing more than just checking your answer in the back of the book, and they may have the answer in base E and your answer is in base 3 or something like that.